Okay, we're looking at the forces and acceleration follow-up. First, we're trying to draw a diagram of the apparatus from the lab. Okay, so we had a cart. There's a force sensor on the cart, and that string ran over to a mass. I'll call that little m. I'll call this one big M. That's the mass for the cart and the force sensor together. Okay, they're going to move this direction. Also, they're both accelerating that direction as we go. Alright, so we're going to draw free body diagrams for the cart and the hanging mass. The cart has a normal force up. This is the cart plus sensor together. Normal force up from the track, weight down, and the rope is pulling it to the right. Because it has wheels and they're pretty good, we're going to assume that there's no friction there. For the hanging mass, oops, that's big mg, not little mg. The hanging mass has a smaller weight because it was smaller than the cart is, but it's accelerating downwards as well, which means it must be unbalanced. This tension must be smaller, so I'm going to go back here and revise this tension, make it a little smaller so that those are equal because it's the same rope. So we see that for the cart, it's in CVPM in the y dimension and CAPM in the x dimension. So we know, because the cart is not accelerating up or down off the plane, but it is accelerating to the right. For the hanging mass, it's in CAPM in the y, and CVPM in the x if you want to say that, but there's nothing exciting happening in that dimension. Which tells us that for the cart, the forces are balanced in the y and unbalanced in the x. Taking the time to think through this will help us out when we go to look at to draw our force diagrams. If you draw your force diagram and it's not balanced or unbalanced as it should be, you need to notice that, and that'll be a spur to fix something. Okay, we're going to write F-net equations for the cart and the hanging mass. So this is just a translation of those diagrams. So in the x for the cart, it's just t, and for the cart in the y, we have n up and mg down. Those are going to cancel out. Now let's look at our directions of positive here. We called up and right positive for the cart, so that means that our acceleration is positive. Well, the hanging mass's acceleration is down. So if we go back to our force diagram, what we want to do is make sure that because that right was chosen, the up and the down here in the cart doesn't matter, but because the right was chosen for the cart's direction of positive, we have to choose down for the hanging mass. So if I have the acceleration to the right and calling that positive, it needs to also be positive for the little mass. Okay, back to here. F-net for the cart, for the hanging mass. Because of that direction of positive, we're going to call it mg minus t. Oh, big M, little m issue there. Okay, so these two F-nets that are unbalanced, Newton's second law tells us that the net force on an object is equal to its mass times its acceleration. So this t for the cart is the cart's mass times the cart's acceleration, and for the hanging mass is the hanging mass times the acceleration. Those are the same acceleration, but the masses are different, so I need to be careful about which is which. Alright, we're going to try to find an expression for the acceleration. We have two equations and two unknowns here. T is big MA, and also mg minus t is little ma. What I want to get rid of is t, because I don't know and I don't care about it. So I'm just going to substitute this in because that's right there for me. So mg minus big ma is little ma. Now I have a in more than one place, so I need to collect all the a's on one side, bring this over. Mg is big ma plus little ma, and I can factor the a out and then divide both sides by that, and I will get mg over big M plus little m. We don't really need a number here. The expression is fine. Now determining expression for the tension of the rope is really easy now that we have this result. I'm just going to substitute it back into there. tension is big MA, which is big M times what we just got, little mg over big M plus little m. So if we look at the units in these two expressions, I have a ratio of the masses, mass over mass, so those units cancel. So my acceleration is the same as the units are the same as the units for g, which is fine because newtons per kilogram, meters per second, and meters per second squared are the same. Over here, one set of the masses cancels out, and then I'm left with a mass times g, which is definitely newtons, units of force.